Welcome back to the architectural primer. Now we are on chapter number 13, self-organizing maps and the architectural notion of AI. Start the environment with this button and then go to the actual chapter. So it's on artificial intelligence. There's some background information. You might be interested in reading this chapter 21 of Big Data and Machine Intelligence in the Atlas of Digital Architecture, recently published. This is what architecture is about in my line of argumentation. And I start with the mathematics of stochastics and statistics and make a clear distinction towards probability, which is not seen like that. And this apparatus I'm referring to if I say that most of AI today is stochastics, which means follows the lines of argumentation of the 18th and 19th century, but it is not adequate for coding today. So we think, if we go here, so this is what for example key concepts are: clustering and prediction. So, and then you already see and the notion of an neural networks. It's the same. So you have input layers and you split in different layers, and then you have your output layers. So you have a problem, you address a certain problem, and then you get a solution. So it's a kind of automatized or stochastically adjusted production line. How to address a problem, how to address a solver to a problem, which always means you are in the domain of time, and this is 18th, 19th century. So this is an engineering tool. So I would say, with our primer as architect, we have to deal with it. So therefore, I would say instead of clustering, it's more about looking what is going on and characterizing it and creating an alphabet to describe what was going on. So what is trained? So in our notions, in our terms, you had the last day, you have the memories of the last day. This is big data. Then there are the dreams of the last night about the memories of the last, or the events of the last day. These are the dreams, ethnographia, orthographia. And now you're equipped with it in the new day. Now you have certain ideas, certain characters, ciphers you deal with. So this is your rucksack for the new day. You go out in the bright sun and start to talk. So therefore I think it's more about this. So it's not about clustering and prediction, which is in the realm of seeing, which is in time, and these are within the engineering production lines, the dreams of the last night. So, but it's more about getting a rucksack and start to talk. So it's a realm of talking to go towards space in our notions. All the algorithms in AI are ethnographia, so generic circulation, circles making straight steps, circulation straight step. So, and a neural network, for example, is a perfect layout of a production line, of a stochastic production line. And all these pre-assumptions, they are in principle not there in a self-organizing map. So you don't make any kind of pre-assumptions. That's structurally, it has no form, or it has a generic form, just a cube of voxels, but that's it. And therefore I would say it's not for example, that's unfortunate as well with a map. So a map tries to make a picture of traces of reality. I think that's not the proper thing. I think it's more a screen. Or I would say it's an alphabet instead of clusters, it's a screen, and it expresses a certain personality. So how to talk as a subject, as an active subject in a world you don't know. So there's no assumption of problem and solving with a SOM in principle, or it's easy to understand with a SOM that it can be used like that. And therefore I think it's most adequate for our talks with orthographia, ichnographia and scenographia. So there's there is some references. It always looks like that. So these are the screens of the dreams about the events of the dreams of the last night, of the events of the last day. So these here, and not maps. And that as all algorithms today, prominent, they had been developed in the second phase of AI. Then there was this winter, and then from 2000 on there's this third phase of AI. And the second one had developed all these tools and these algorithms. And in this case, it's Toivo Konen in the 80s. And interestingly, they don't get prominent. So they are not referred. So their development, their contribution to AI are not honored in a proper way. So it's always hidden with this agitation today to get prominent and to push things, to claim scientific ground and so on. So that's a little unfortunate in all these developments, and I think it's important to understand that if you want to to reason about AI, you have to find the algorithms in the 80s, and then you have to find the mathematics in around 1900, and then you are safe. And then you have to find the line. This is what I described here in this chapter. The line towards towards mathematics, and then it's important to find the sources with Bernoulli and Leibniz some 250, 300 years ago. With the mathematics, then go for these lines and don't get blind with a little wild satiric activations or in science today. So it's all not this new, and it's new in this fertility and this performance. So with these CPU graphics cards of NVIDIA and so on, this is new. It's an amazing speed. That is more a technical trick. If you want to go for that conceptually, you have to go back. So nevertheless, the SOM is not the most prominent algorithm, but I think it's most adequate to follow our lines of argumentation. So there's no principal difference in all these methodologies, of course not, but this is most adequate to understand and be astonished about why the hell is this working. These are all the scientific articles, so there are a lot. So get this, look a little around. So this is my favorite algorithm because it's architectural. Don't make any pre-assumptions, and we easily can separate this algorithm from the scenographia and from the code we are interested in. Good. Now, this is the code from scratch. That's important. So I don't need a lot. let's go and copy it to our desktop. No, I think we can do it here in the cloud. So evaluate that. So there's a data structure needed. So this is hidden, so it's internal. It's a data structure. So just very simple grid of things. We will have a picture of that. This is the actual training, the actual algorithm, and it's just this. That's the algorithm. And it's with all these algorithms. They are very recursive. It's complicated to make them fast, so you have to know a lot about computing itself. But logically, it's very few formulas. So it's always just this. So the same with whatever you do, random forest, neural networks, whatever. They are this size. Google is working with, I always say these are crystals in light, emitting images of the world. So they are very fast. And it's always like this. So this is a poem, and it's a crystal doing it. Then there's some helper functions, and not important. And then this is the interface. So you see interfaces, and we wrap this in this case as a function to work with it in Mathematica, this cloud environment. So but this is a code needed to do AI. Very important. So let's have a look how it works. Set up a SOM. So we always have data. So this is a memory. The last day, or big data. This corresponds to big data. So and this is cultural heritage. So in this case, we make we do a 1,000 three-dimensional real numbers between 0 and 1. And you can imagine now we look at the first 12 of these numbers and render them as colors. So these are the colors. Good. That's the cultural heritage. So this is our SOM of a specific size. This is a dream. This is machine intelligence. And this I would say is urbanization, or the global industrial globalization of the industrial infrastructure as a new fertile landscape 2.0, or however we want to say that. So we had this kind of discussions. So this might take a long time, but now this is very few. So go here and say show the actual status, and now this you create. So now we are dreaming about of the last day, and you're putting that into a screen of 8 by 8 by 3 dimensions. So it's 8 by 8 by 3 dimensions to make that a screen. So now we're training, it's done. So it's super fast. So this is how to set up the system. Now, first it's about characterization. So I would say this is a kind of clustering, but clustering plays at night, and characterization is towards an alphabet can carry around to be able to talk about something, so that this persona is able to talk. So what is the thing doing? So this is an array of 8 by 8, so this screen. So now we can ask if there is at the new day a vector, for example, red, green, blue, so this is red, then he says my red is at screen point 38. So we will see how this works. So, and we can say, what is your dream of that? What did you dream about that? So then you say it's 100 SOM, and then you say, he said, this is what what I dreamed, or what I remember with my dreams. So they always fade a little out because each of these cell of the screen is somehow connected with the others. So, and therefore it shrinks a little. In principle, we could expand it again, but now let's show. And this is the memory. This is the character of the dreams of the last night. So there's a word, what you understand about, so what this persona here woke up, goes out to the bright sunlight, what this persona understands with the physicality of red. And he says, okay, it's this. So we can ask for the screen. It's this. So what you see is there had been random numbers, 1000 random colors, and this is a screen. So which means we get this machine gets a kind of understanding, represents an understanding. So it processed with its dream whatever happened at the last day, and says, yeah, this is all my memory. This is my understanding of the events of the last day. And this is my screen. So which means, so we can say 38, 1, 2, 3, 8, this is my red. That's the most red character of my dreams. Good. And you see it got an understanding of the spectrality of colors of the last day, because we had colors here. So without telling it. So it's a spectrum of so it's a spectrality of what happens around. So you can make it smoother if you run more, but this is not a key problem. So it's a very rough setup. So, and now you can ask, for example, the samples of, what was it here, 3.8. It's always different. If you run it then by your own, you will have another map, another screen, because it gets another persona. And these are the samples. So we had 1000 here, 1000 samples, and these are the samples this character processed or characterized. So, and we can ask for the samples of this color. It's the same. So it's another way how to do it. So we say, if there's a new event, red, what is your memory of this? What is, or which indexes towards big data are that? And then you say it's this, and here you get the colors which constitute the character red. So it's a range of things around the new event. So this is how this active subject remembers, or what it knows about this new event at a new day. So these are the indexes to the events of the last day to give you some advice for the new day. So this is what he remembers. So that's like this. So I'm describing it in our terms. It's not like described like that in literature. It's important to know. But I think this is most adequate. Good. Now we want to use it. What I can say, for example here, SOM of 1, red, green, blue, and I don't know the blue. So, and he's saying, this is what I remember. This is my character. So this is the character of this is the character corresponding to this element on the screen towards this vector with missing under other vectors. So now I can ask, give me samples. What do you understand? What would you do? And then you see that these are the samples, and we can get for so he says I'm seeing, so if this is missing, or if it is hidden, then this active subject will expect these colors. So this is about articulation. So he says in the words of this, so if you ask this, he says this. Okay, that's it. The interesting how it works, we can show it. Where did we have? We set it up here, so we can say SOM map. So these are the three-dimensional. This is an array of three-dimensional vectors, which constitute the image we'd seen RGB. So, and this image, this can be shown as image 3D of that, and then you see this is a kind of the brain of it. Of R, G, and B. And you see they are structured. It's not random. Or we can go for slices, then we make image of now we have to, yeah, that's too much, doesn't help. Good. So that's the data structure. It's just this grid, three-dimensional screen of elements and done. So, and the training algorithm is at this. They have it here. Training algorithm is this. So you have this screen of random numbers initially. So therefore white noise. And then you put in these events of the last day, the vectors, and then you throw like a stone into water. You throw a stone into this screen, and then the stone hits the water at the pixel of the screen, which is nearest as a vector to this screen, in color to this screen. So it hits it there, and then there's a wave, a little. So therefore it affects with these colors the neighbors of the colors. So then the next stone comes, a blue one, then it hits the most blue pixel of the screen, and it makes a small wave. So that everything gets around this most blue point gets bluish. Then green pixel, greenish around. And if you do that for thousands, 10,000s of time, this screen gets adapted, and that's the screen of the dreams of the last night. Good. And then it's an instrument to play, which means we have to, we start and say, what did you dream about the last day? And what can you tell me about the new day? About this actual situation at the present day? And then he says, I think it's something like that. And then you have these examples to discuss. So now this is an abstract example with colors. Now make a car driver to see that's always the same. Any kind of application can be written like that. That's the astonishing thing. So here, for example, we have traffic lights, green, yellow, red, and then we have events. Though this is all the good driving of the last day. Traffic light is green, speed limit is 50, speed is 20, brake is 0, gas is 20, and this is good. So we only have 20 different of these events. So this is the big data. So evaluate that as a data set. So we can now let's go here for the driver. So now we make a vector. These are the vectors. This is readable. This is just vectors, and instead of 3 dimensions with the images, now we have 6 dimensions. And of course, in an actual car, you have thousands of dimensions because you need cameras and blah blah blah. So, but here it's 6. The principle is the same. It's 6-dimensional, and we have a small screen. It's 6 by 6. And if you have a car driver, you have a bigger screen, higher resolution in vectors, but it's the same principle. So then the driver is the same as we had. So we create the driver. Now he's dreaming of these events of the car driving of the last day. And here you see the map now of his brain. You see it's structured. So this is the screen, which dreamed about the driving of the last day. And now you put it into a car, and with the actual events, you know the traffic light is red, speed limit is 70, speed is 50. You don't know whether to brake or how much, or whether you need gas, but it should be good. So which means this is our vector. Missing, and so on. So now we simply say drive vector, driver vector, and then you get this. Like so he said, this is my memory. Like we had it here with the colors. Complement the colors. Now we complement the gas and the brake. So he says, this is most likely what I remembered from the last day to a situation like this, which is incomplete. So this is just to render it so that we can read it. And he says, brake is 97, so you have to brake, and there's no gas. So which, because traffic light is red. So now, let's go, for example, switch the traffic light to green, and see what's going on, and then you say gas 45. And you can go to things you don't, so for example, now we can go for speed 86, and there's a limit of 70. So, and what do we do? And then he says gas, brake, and so on. It's not too funny. Speed limit is at this. And now he says brake, go down. And he never seen a speed of 86, for example, in the example before, but he's working reasonable. Red, then we go here and say go stronger. So that's it. So the fascinosum, and this took us or me, I'm still puzzling. How is it working that if you have a screen like this, you just throw in the events of the last day, the big data elements, and then you're dreaming like this, throwing here, 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 like it's raining, and collecting all this. How is it working that this got smart? And this was the reason why we went first to these metaphors with the dreams of the last night, the memory of the last day, to get an understanding of that. And why I think it's very important to understand what are numbers, what are ciphers, what are characters, what is the difference between arithmetics and geometry, what is the difference between time and space and so on, just to get an understanding that this simple arithmetical throwing of vectors into an array of vector and a little adapting it in a Gaussian curve from stochastics. It's that's it. And I think, yeah. And remember that you can address any kind of problem because you abstract from problems by this. That's the same with AI, with all AI. So this is why Google can drive cars, sell books, go for chess, or translate languages and whatever. Because it's out of the realm of problems, which is interesting for architects, because then you know the operability of ichnographia, and you can start to articulate the scenographia. But you have to get rid of these, which is all across in AI, about the notions of clustering, which is set theory, prediction, which is stochastics. So even the applications of AI are wrongly, so they get very tyrannic by the way that they simply automate everything, and they simply say, if you're not following these lines, you're kind of silly. So this is the situation today. It's very interesting, and it takes a lot of meditation to believe that, yeah, this is the power of numbers. They can do that. They can do whatever. They can do everything. And you have to reason about what should they do, the noble architectural question. Thank you for watching. We will go to more detailed, more complex examples and applications, not how to use AI, not especially the self-organizing map. Bye. See you.